These are notes on zooming into a cloud, or essentially interactions with different measurement perspectives. So you've watched the Powers of 10 video, and you've sorted things based on not different measurement scales. I mean, all of these are distance, right? And they're all meters, but kind of different perspectives. Are we talking about macroscopic or microscopic or large scale or atomic molecular? Technically speaking, you could use any of them, right? I could tell you I ran 0.0000 of a megameter, or I guess 0.0001 of a megameter, and that's not really helpful because you don't have a perspective for that. But if I told you I ran a certain number of kilometers or a certain number of meters, you'd have a perspective. So really these are measurement perspectives, not different scales. So let's look at what happens as we zoom into a cloud. So we're going to kind of combine the measurement, different perspectives on measurement with the chemistry that we're looking at in biology. So just kind of a question, does air have mass? So if you look at this jar, is this jar empty or is it full? And you know, pause the video, take a second, maybe write down whether you think it's full or empty. So let's look at air. So on a large scale, we look up in the sky, we see clouds. And so let's get a pen here. And so this, when it's saying 10 to the third, this would be kilometer, okay? So this would be 1 kilometer. And we can talk about looking at clouds or a portion of sky over a kilometer. So, you know, this box here denotes about a kilometer, and that's large scale. And we see these clouds and we know what the clouds look like. So as we zoom in closer, so this, now remember this is 1 meter, so this would be 1 centimeter. It's still macroscopic. We can see something that is 1 centimeter. We have water droplets, and those water droplets are in the air, and they're usually quite large for a droplet, and so these actually fall to earth, and so we would call these actually raindrops. That's what a raindrop is, okay? All right, so then water or air also contains water droplets. A water droplet is smaller than a water drop, okay? Hence the cute little suffix let, droplets. And those are on the order of about 1 millimeter. Okay, so down here would be 1 millimeter. And, you know, so 1/10 of a size of a raindrop. And that's actually what clouds are made of. So a lot of people think clouds are water vapor. It's not. It's actually tiny droplets of water on the order of 1 millimeter, still macroscopic. I mean, we can actually see them. And if you've ever kind of driven through a fog bank, or especially walked through a fog bank, same thing, it's a cloud on the ground, you can actually see the individual particles. They're itty bitty, you know, they're only like 1 millimeter, but those are actual droplets of water. It's not water vapor. Water vapor would be gas. We can't see water gas. Water is colorless, and so when it dissolves in the air, I mean, think about, well, actually look around wherever you are right now, unless you happen to be in like a steamy bathroom because you just took a shower and now you're listening to your biology notes, you probably can't see the water in the air around you because it's evaporated, it's gas. So the water that forms clouds is actually liquid water, it's droplets of water, and it's held up by essentially a network of air, which is why it stays up in the atmosphere instead of falling down. As those droplets combine together and make drops, they get heavy and then they fall. So we actually call that a suspension as far as mixtures and things like that go. But now we can get down to the microscale. So if we look at the microscale, so this down here is 1 micrometer, and a micrometer, we use this funky Greek symbol which is like a U with a tail, and then an M for meter. So that's 1 micrometer. And that would be 1/1,000,000th of a meter. This is now the microscale. We can't see this without a microscope. And now we're getting down to like this would be 1 droplet. And you'll notice 1 droplet has, you know, millions of actual water molecules in it. And then here would be 1 water molecule. Now that we're not going to be able to see. That's going to be the dissolved water in the air, the stuff that's evaporated. And then here, this is probably the oxygen. That's probably nitrogen. Well, this is tough to say. This is going to be oxygen, and I'm telling this, I can tell this because of the blue, although normally oxygen is represented by red, but I can tell this has got to be the blue. So this is going to be the oxygen, this is going to be the nitrogen, here's a little carbon dioxide. We're missing the argon. There's quite a lot of argon compared to other things in the air. So that would be 1 cloud droplet. This is the actual droplet here in the air. And then if we zoom even smaller, so this is the micrometer, so this is a nanometer, and that is with an NM. And this is now the atomic molecular scale, meaning, you know, while this is, we still see water, we can't actually see water. We have absolutely no tools available that can show us 1 water molecule. But that's if we zoomed into the droplet, we could see 1 water molecule. And so that would be the hydrogen and the oxygen and another hydrogen, and this would be the bond. Now remember, water is covalently bonded, so what's actually happening here is that this is, if you go back to the water notes, let's say this is a hydrogen and they're sharing these 2 electrons, and this is a hydrogen and they're sharing these 2 electrons, and then water's got this, these are the valence electrons. Oxygen has these here. So if you remember, we talked about that when we talked about properties of water. And we're going to be talking, when we're looking at chemical energy a little later in this unit, about energy having to do with the bonds, which is why in this PowerPoint you can kind of see these bonds here, because we're going to be talking about what kind of energy is required to break those bonds, what kind of energy is released when you form those bonds, and things like that. So the bonds are actually important to the story. So there's other molecules in the air. There's oxygen, which is O2, and that has what's called a double bond, because you can see there are 2 bonds between the oxygens. There is carbon dioxide, and you'll notice that each carbon is double bonded, or I'm sorry, the carbon is double bonded to each oxygen. So this, we would say, are 2 double bonds. A double bond is not 2 bonds. Water has 2 bonds. A double bond is a, well, let's just say it's a double bond, but it's still between 2 atoms. And when you take chemistry, maybe not even high school, if you go into college chemistry, you'll learn about things called sigma and pi bonds that are what makes a double and triple bond. We're not going to worry about that. Way above our scope. And then we have nitrogen, which actually has a triple bond. So we've got 1, 2, 3. So it's still between 2 atoms, but there's something going on that makes it a triple bond. And as you might anticipate, a triple bond is stronger than a double bond is stronger than a single bond. Sort of doesn't matter. These are all on the atomic molecular scale. So then our atmosphere is about 78% nitrogen. A lot of times we'll round up and say 80%. It's about 21% oxygen. A lot of times we round down and say about 20%. The next compound or element or molecule, and I'll talk about that in a second, in like the next largest percentage is actually argon, and that's 0.9%. And argon is interesting because argon is a noble gas, and so it doesn't bond with other elements. You may remember that. And so argon is the only one of the top three things, nitrogen, oxygen, argon, that is actually just an atom because it doesn't bond. It's just argon atoms. A lot of lights are filled with argon because it doesn't react to anything and it's found in our atmosphere, so you can get it rather cheaply. Then the carbon dioxide that we talk so much about and that we focus so much on is actually just 0.03% of our atmosphere. It's not a lot at all. I think sometimes we get this view that it's, you know, really prevalent in our atmosphere, and it really isn't. But it has a big effect. The nitrogen doesn't have a huge effect on our atmosphere. It's the carbon dioxide that does, because the carbon dioxide is a greenhouse gas, which means it traps heat from the sun in our earth, which we need. If we didn't have it at all, it would be incredibly warm during the day and incredibly cold at night. We actually want that carbon dioxide to trap the heat and regulate our temperature, but if we get too much, then it gets too warm. Okay, we like a little heat, obviously. I mean, think about your house. You want your house comfortably warm. You don't want it uncomfortably warm. And then water is actually not generally listed as a component of air, and this is the reason, because it's variable. It depends on how humid the air is. You can have an incredibly dry climate where there's very little water in the air. You can have a very humid climate, think like a rainforest biome, where there's a ton of water in the air. In some places it can vary from day to day. Some days it can be really humid, some days it can be really dry. It can vary seasonally, whereas these things do not vary. Now, obviously, carbon dioxide, we've added more carbon dioxide, but I'm talking they don't vary naturally from season to season or biome to biome, whereas water really does. So I know some of you asked on the pretest what it meant by dry air. That's air without water in it. Pure air has no water in it. So that's kind of interesting because we think about water as being a component of air. So then let's take a look at this idea. Let's go back to here. What's the difference between an atom, a molecule, and a compound? So I'm going to have kind of a little key here. So atoms, when we're talking about atoms, we're talking about elements from the periodic table that are not bonded to anything else. So I'm going to underline the atoms. Actually, what I would recommend doing is pause the video, write these down, and you underline the atoms. Okay, so you should have underlined oxygen, argon, hydrogen, carbon, and nitrogen. And in our atmosphere, none of these exist with the exception of argon. Okay? Argon is the only one right here that's actually in our atmosphere in atomic form. The others are not. So then let's jump to a compound, and we're going to put a box around compounds. And so a compound is when atoms are bonded together, but the atoms are different types of atoms, so it's not all the same type of atom. So go ahead, again, pause the video, and put boxes around the ones that you think are compounds. So you should have put boxes around carbon dioxide and water. Both of those are compounds because they are different elements bonded together. So in carbon dioxide's case, we've got carbons and oxygens. In water's case, we've got oxygens and hydrogens. And finally, we get to molecules, and we are going to circle molecules. And molecules are any atoms that are covalently bonded. Now, we've talked earlier about covalent bonding being a bond where electrons are shared between two atoms. And it's a little difficult to tell simply by looking at this whether these are covalently bonded or not. They could be covalently bonded, they could be ionically bonded. And so in order to figure that out, we really need to go to the periodic table. So here we have the periodic table. What happened to my pen? And on the periodic table, we have some compounds that are metals and some compounds that are nonmetals, and then some in the middle, which are these weird things we call metalloids. So more or less, I'm not going to get into technicalities here. If you really care, you can look it up. But more or less, if we draw kind of a diagonal line down, starting at boron and just going down diagonally, everything over here are nonmetals. These are our nonmetals. And everything over here, with the exception of hydrogen, hydrogen actually is a nonmetal. Everything over here, including this stuff down here, are all of the metals. And things that bond covalently, a really good rule of thumb is if it's covalently bonded, it's a nonmetal bonded to another nonmetal. If it's ionic, it's a nonmetal bonded to a metal. And in biology, we don't deal with a lot of ionic compounds. We're going to talk about a couple when we talk about cells and cell membranes, but by and large, in biology, we talk about nonmetals bonded to nonmetals. So most of the things we see that are bonded in biology are bonded covalently. And you'll notice there are far fewer nonmetals than there are metals, which is why we see so many of the same elements showing up over and over and over again. Because while we can combine these in millions of different ways to make millions of different molecules, there's only a few atoms that we actually have to work with. Whereas when you get into ionic compounds, you have just so many more atoms that you could work with. So, knowing that, going back here, if we know that a molecule are any atoms that are covalently bonded, meaning a nonmetal bonded to another nonmetal, go ahead and circle those. And I don't know what happened up here, but I'll circle them. So we have oxygen, and we have nitrogen, because those are both nonmetals and they're bonded to themselves. But then we also have carbon dioxide, because oxygens and carbons are nonmetals, and we have water, because hydrogens and oxygens are nonmetals. So this is where you can see carbon dioxide is a compound and a molecule, whereas oxygen is simply a molecule. And often we will call this oxygen gas, because in our dealings with it, you can certainly have liquid oxygen, you can have liquid nitrogen, but in everyday life, we normally encounter these as gases. So sometimes we'll call this nitrogen gas and oxygen gas to differentiate between nitrogen, the atom, which we don't really come across in everyday life, and oxygen, the atom. So this should also help you answer the warm-up question from Monday as to what's oxygen. And then just briefly, something that would be a compound but not a molecule is any ionic compound is going to be a compound because it's a metal to nonmetal, so they're always going to be different atoms, but it's not covalently bonded because it's ionic. All right, so please feel free to comment on, not comment, but add questions to anything that you have, and you can put those right on to the YouTube or ask them in class.